All right. Hello, everyone. Welcome to Chapter 7 of Designing Data Intensive Applications. In today's video, we are going to talk about transactions. So, if you have been coding for a while now, you would have used transactions in various scenarios for various reasons. But here's the thing, a lot of engineers, including me, at some point, we don't really stop to understand what kind of guarantees does a database provide when you use a transaction. So in this video, we are going to break that open. We'll understand what transactions actually protect you from and what they don't, and why different databases make different trade-offs. By the end of this video, you'll know what isolation levels to pick, what locks to use, and also the why behind those decisions. So let's get started. All right. So let's first understand what a transaction actually is. A transaction wraps multiple operations into one atomic unit. What that means is either all of the steps in a transaction succeeds or none of them do. The classic example here is of a bank transfer. So let's say Alice wants to transfer £100 to Bob. If we were to implement this, here's what would happen step by step. First, we would read the current balance in Alice's account. Then we would deduct £100 from Alice's account. Then we add £100 to Bob's account. And then finally, we commit. But what all can go wrong in this particular scenario, right? One is the write to Alice's database could fail. There could be a DB connection issue, there could be a query failure, or n number of things can happen. That's one scenario. Second scenario is the write to Alice's the Alice's transaction or the Alice's account balance that succeeds, but the write for Bob fails. Now the money has left Alice's account, but Bob has never received it. And that's another scenario. The third scenario is what if both the writes succeed, we commit, but then there's a network cutoff before the database can tell the client that the commit actually succeeded. So the data is correct, but the client doesn't know that, and the client can retry. Now, when the client retry, it might show an error, or it might process the whole transaction again, leading to deducting £100 again from Alice's account and adding £100 more to Bob's account. Right? So, how do you handle all of these scenarios? That's exactly where ACID comes into picture. Each letter in ACID is a specific guarantee that the database makes to protect you from one of these failures. So let's go ahead and understand them one by one. All right, so we will start with the first property, that is atomicity. So atomicity means that if any operation in a transaction fails, either via a network error or a crash or a constraint violation, all of the writes that have happened so far gets rolled back. The transaction either completes fully or it leaves the data exactly as it was, as if nothing happened, right? So going back to our Alice and Bob's example, if Alice's balance has been updated but the write to Bob's account fails, Alice's rights gets rolled back. So you don't end up in a state where money has left one account but hasn't arrived in the other, right? Now moving on to consistency. Consistency means a transaction must move the database from one valid state to another, keeping all rules, constraints, and invariants intact. So take a simple example. An account balance cannot go below zero, right? You cannot have a negative account balance. Like in some scenarios, you can, but let's consider that example that in our scenario, the account balance cannot go below zero. If Alice wants to transfer £100 to Bob, but Alice only has £60 in her account, when the transaction tries to deduct £100 and the balance goes negative, the database will reject it. That constraint is violated, the write fails, and the transaction doesn't go through. But here's the important thing to note in case of consistency. The database can only enforce the rules it knows about. So it is the developer's responsibility to define those constraints in first place. The database doesn't inherently know that a negative balance is invalid. It knows because you configured it or you told the database that this is a constraint which should not be violated. So, consistency is kind of a shared responsibility where the database holds up the rules. Databases upholds the rules, but the rules are defined by the developers or by the engineers. All right, now let's talk about the next guarantee, which is isolation. So, isolation matters when you have concurrent transactions. Concurrent transactions meaning two or more transactions running at the same time. Now, the idea here is that each transaction should execute as if it's the only one running. So, it shouldn't be affected by what other transactions are doing in parallel. So, back to our example, Alice is transferring £100 to Bob. At the same time, John is also trying to transfer £100 to Bob. Now, both the transactions are concurrent. Let's say Bob's balance start at 100. Now, the first transaction reads Bob's balance as 100 and it updates it to £200. Second transaction is not aware that the first transaction has updated, is also updating in parallel or has updated the balance to 200. Second transaction also reads the Bob's balance as £100, and so it also updates it to 200. Now both the transactions have committed, but Bob only receives £100, not 200, and one transfer is lost in the scenario, right? That is exactly what isolation is designed to prevent. And the strongest form of isolation is serializability, where the result looks as if two transactions ran one at a time, not concurrently. And in the serialized version, the second transaction in our scenario would only start after the first commits. So the second transaction would read Bob's balance as 200 and it would update it to 300. And both the transfers would land correctly. We'll get into exactly how these databases achieve this and what are the trade-offs involved. We are going to talk about isolation in the entire video. But before getting into it, we just have to touch upon the last guarantee, which is durability. So, durability means that once a transaction has committed, the changes are permanent. Even if the database crashes immediately after, the data survives. That's the guarantee which the database provides you or should provide you. So going back to Alice and Bob, the transfer completes, the commit goes through, and let's say split second later the server crashes. When the database comes back up, Alice's balance should still show 400 and Bob's should still show 300. The commit happened, and that's your way to know that your data has been saved in the database. But how does the database guarantee this? So through something called as write ahead log, we have discussed write ahead log in our first few sessions. So before any change is written to the actual data files, it is first written to a log on disk. So even if the server crashes mid operation, when it restarts, it replays the logs and recovers to the last committed state. So durability is database's promise, it's database's responsibility, and it's a guarantee which the database should provide you. Now, moving on to isolation, right? So we have covered atomicity, consistency, durability. These three are relatively binary. The database either upholds them or it doesn't. Uh, you'll get them as part of the deal. But isolation is different. Isolation is a spectrum, and this is where things get interesting, things get complicated, because full isolation, as I said, full isolation or the strongest form of isolation is serializability, but that is expensive and it hurts performance. So database gives you choice of how much isolation do you actually need, and different choices protects you from different kind of scenarios. So now we will understand what different isolation levels actually guarantee and what they don't, and how to make that call in your own systems. All right. So let's talk about isolation levels. The strongest guarantee, as I said, is serializability. Transaction runs as if they are sequential, one at a time, no overlaps. But to achieve this, readers have to block writers, writers have to block readers, and then that in this scenario, deadlock becomes possible. And in high traffic, this kills throughput, and this simply doesn't scale. So database offers you weaker isolation levels that prevent the most common problems, and then let the application handle the edge cases. So let's understand them one by one, starting with the most common, which is your read committed. Read committed is the default in most databases. It makes two promises. One is you will never read the data that hasn't been committed yet. And second is you will never overwrite the data that hasn't been committed yet. So, no dirty reads, no dirty writes. So, let's first understand what dirty read means. So, we'll talk about the same scenario where we are transferring £100 from Alice's account to Bob's. Now, when we spoke about that, we spoke about three steps. First one was to read the account balance in Alice's account, then deduct £100 from Alice's account, and then add £100 to Bob's account. Now, let's say the second step succeeds where the amount has been deducted from Alice's account, and the third step is in progress. Now, at this point, Alice goes ahead and she tries to view her account balance and she sees 400. Now, this 400 is a dirty read because the transaction is not committed yet. What if the third step fails and we are not able to write successfully to Bob's account? Then this whole thing would be rolled back, right? So the read would have acted on a data that never existed. So that is a dirty read. Let's now understand dirty write. So dirty write is related, but it's a bit different from dirty read. So instead of reading uncommitted data, you're overwriting it. Let me show you exactly what that means with the car sale example from the book. So if you see over here, the scenario is that Alice and Bob both wants to buy the same car at the same time. Now, when you buy a car, the database here needs to update two things. One is the listing tables, which records who the buyer is, and the other is the invoices table, which records where to send the bill. Now, both of these rows needs to stay in sync, and that's the invariant over here. So let's see. Both the transactions begin. Now you can see that Alice transaction A has updated the buyer in the listings table as Alice. Transaction B then overrode the transaction A's uncommitted data and it has updated it to Bob. So this is one example of dirty write. Then transaction B was a bit faster. So transaction B updated the invoices with billing address as Bob. And then transaction A overrode the billing address to Alice. Now, when both the commits succeeded, no error is thrown. The database accepts both the transactions, but the data is inconsistent. So if you see over here, the buyer is Bob, buyer is listed as Bob, but the invoice address is of Alice, right? So Bob buys the car, but Alice receives the invoice of it. And this is the key thing to understand about dirty writes, that neither write was individually wrong. Transaction A writing Alice as a buyer was a valid operation. Transaction B writing Bob as the buyer was a valid operation. The problem happened because they were writing to the same rows without any coordination. And each transaction was stepping on others' uncommitted work. Now, read committed isolation prevents this with row level write locks. So when transaction A writes listing buyers equals Alice, it holds a lock on that row. Transaction B has to wait until transaction A either commits or aborts before it can write to that row. So row level locks are for writes, and for reads, the database simply remembers the last committed value and serves that until a new commit lands. Now, the problem with read committed isolation level is read skew. Okay, now let's understand what read skew means. So, Alice has two accounts. Account 1 has 500, account 2 has 250. The total balance of the two accounts is 750. So, now transaction A is a read where Alice is checking her total balance and it reads account 1 and gets 500. At the same time, another transaction starts, transaction B, and it transfers £100 from account 1 to account 2 and it commits. So account 1 now has 400 pounds and account 2 has 350 pounds. After this, the transaction A reads account 2 and it gets 350 pounds because that commit already happened. Now transaction A sees account 1 as 500 and account 2 as 350. So the total here is 850, which is wrong, right? So what has happened is your transaction 1, transaction A started, it did a read on account 1, and then transaction 2 started, committed, and then in the same transaction A, there was a second read which happened on account 2. That read a committed data. So it didn't perform any dirty read or dirty write, but because of the time span between the time between two reads, there was a commit which happened between two reads that caused that anomaly. Now, in this scenario, this is fine. So, after some time, if you refresh, the account balance would then again become 750, right? It wouldn't be a problem. Eventually, the data would become consistent. So, for short transactional operations, you can live with the read skew. But there are scenarios where read skew become a serious problem. The first one is backups. When you take a database backup, you're reading large amount of data over a period of time, and it's not instantaneous. It takes time to for those backups to complete. So if writes are happening concurrently, then your backup will contain data from different points in time. So rows reflect the state before a transaction, and there can be rows that reflect the state after a transaction. So if you ever restore from that backup, your data is internally inconsistent. Let's understand this with an example. So I have two accounts, account A and account B. Both have 500 pounds. So the total balance which we have is 1000 pounds. Now at 12 o'clock, my database backup starts. It's a large database. It is going to take time for that backup to happen. It reads records progressively, not all at once. Now at 12:01, the backup reads account A and records the balance as 500 pounds. While the backup is still running, a transfer happens. I do a transfer of 100 pounds from account A to account B. The transaction commits, and then account A now has 400 pounds, account B now has 600 pounds. The backup is still ongoing, and the backup now reaches a point where it reads the balance in account B and it records it as 600 pounds. So, what does my backup at this point contain? It contains account A balance as 500 pounds, account B balance as 600 pounds, right? So, the total is 1100 pounds over here. That is wrong. And this 100 pounds, it has appeared from nowhere, right? You cannot balance this, like you cannot figure out where this came from. And if I ever have to restore from this backup, then my database is will be in an invalid state, and I would have no way of knowing why or where this 100 pounds came from, right? So this is where like both the reads were of committed data, no dirty reads happened, but the backup captured two accounts at two different points in time, and the transfer that happened in between made the number inconsistent. And this exact problem is solved using snapshot isolation. So, what snapshot isolation does is instead of reading whatever the latest committed value is at the moment of each read, every transaction, or in this case, the entire backup process, reads from a single consistent snapshot taken at the start. So, account A and account B are both read as they were at 12 p.m. before any transfer happened. So, in this way, the backup is internally consistent. This leads us to snapshot isolation, which is the second isolation level, which we are going to talk about. In snapshot isolation, as I said, each transaction reads from a frozen snapshot taken at start of that transaction. The database keeps multiple versions of each row, and this is called as MVCC, multi-version concurrency control. Even if other transaction commits while yours is still running, you keep seeing your original snapshot. And this is why your Postgres calls this isolation level as repeatable read, because no matter how many times you read the same row within a transaction, you will always get the same value. So this solves our backup problem completely. The backup process reads from a single snapshot at the start, and no matter how long it takes, it sees a consistent view of the database. But snapshot isolation has problems of its own. So, two transactions, consider this scenario like two transactions can both read the same condition, both decide it's safe to act on it, both write, and together they violate an invariant that neither write alone would have violated. This is called as write skew. So, let's now understand what write skew is. But before we get into it, so snapshot isolation gives you three promises. It prevents you from dirty reads, dirty writes, and read skews. And the trade-off is write skew. Now, to understand the write skew, we'll take another example. So the book talks about a lot of examples, and it really helps you understand all of these concepts. So the book mentions the example of on-call doctors. So the scenario is of an hospital. In a hospital, uh, there has to be one doctor on call all the time, and that's the rule. So doctors can go off call if they are unwell, but someone has to be available. The current state of our database is that both Alice and Bob are on call for the night shift. So we have database entry, which we have a column which says on call, and that on call is true for Alice and Bob. Now Alice feels sick. She starts a transaction to mark herself as off call. Her app queries the database. The query first checks how many doctors are currently on call. The database returns true. Condition is satisfied, so the transaction proceeds and marks Alice as off call. At the same time, Bob also feels sick. He starts the same transaction. His app also queries the database to check how many doctors are on call. It returns 2 because Alice's transaction hasn't committed yet. This started before the Alice's transaction was committed. Now, both Bob's snapshot shows both doctors are still on call, so the condition is satisfied and his transaction also proceeds. Bob is marked as off call. Both the transactions commit successfully. Now, the scenario is that the hospital has 0 doctors on call and the business rule is broken over here. So, let's first understand why snapshot isolation couldn't catch this. Because Alice updated her own row, Bob updated his own row. So, if we saw that the read committed isolation and snapshot isolation, they work on row level locks. Now here, alice alice record is one row, Bob's record is another row, right? So we are updating two different rows, but the condition is on the database as a whole, on the table as a whole, right? So both transactions were perfectly valid in isolation. It's only when you look at what they did together that the variant breaks. This is right skew, and it is fundamental limitation of snapshot isolation. The only way to prevent this is to go with serializable isolation, which is what we are going to go into next. But before we get into serializable isolation, let's understand the pattern that causes right skew, because it is because it almost always follow the same structure. So you perform a select to check a condition. Based on the result, you decide to make a write, but the data you just read is being changed by another transaction at the same time. So by the time your write commits, the premise you base your decision on is no longer true. This pattern has a name which is called as phantom. So a phantom occurs when a write in one transaction changes the result of a search query in another transaction. It is called as phantom because from your transaction's perspective, row appears or disappears that weren't there a moment ago. So the key difference from other concurrency problem is that most race conditions involve a conflict on a single row. Two transactions trying to update the same record. Phantoms involve a search condition across multiple rows. It is not about one specific row changing, it is about the overall result of the query changing underneath you. There are few ways to deal with phantoms problem. The first is serializable isolation, the only level that is guaranteed to catch all of these cases. We'll get into serializable isolation shortly. Then the second method is explicit locking. So whenever you are performing a select statement, you add for update to your select statement, which tells the database that I'm reading these rows with the intent to write. So you lock them and don't let anyone else change until the transaction commits. Then the third is materializing conflict. So sometimes there is no existing row to lock. So the phantom is about a row that doesn't exist yet, right? So in that case, you create a placeholder row just so you have something to lock. So let's understand this with the room booking example. So let's say Alice wants to book room 1 at 2 p.m. and her app runs a query something like select star where room is 1 and slot is between 1 and 2. That returns 0 rows, so no booking exists. The app thinks that slot is free and goes ahead and inserts a booking. Bob wants the same room at the same time, so his app runs the exact same query and also gets 0 rows. Also thinks that the slot is free and then it inserts a booking as well. Now room 1 is double booked. Now you might think that what if we update for update to that select? That would lock the row and prevent the conflict. But here's the problem. The for update can only lock rows that exist. There are no rows to lock here because there is no booking in the database, right? So the conflict is on a slot that hasn't been booked yet, and that's the phantom. Materializing conflict is the solution. So instead of treating a free slot as an absence of row, you you actually add those real rows. So you create a room slots table upfront with every possible combination of room ID and time slot. So you'll have rooms with ID 1, 2, 3, 4 with slots of 8 to 9, 9 to 10, 10 to 11, and so on. Right now, when Alice goes and queries for room 1 at 1 p.m., then the actual row to lock, and then there's an actual row to lock with for update. So when Bob's transaction hits that lock, it has to wait. But as you can see, this doesn't seem like like it seems like a more complicated, painful solution because you're managing a table with every possible slot for every possible resource, and it adds unnecessary complexity and maintenance overhead to your system just to work around or database limitations. So this is why in such scenarios, most developers, engineers prefer serializable isolation because the database handles all of this phantom detection under the hood. And you don't need to create extra tables or manual locking. You just declare the isolation level and let the database figure it out. Now, let's get into serializable isolation and let's understand how it works. There are three approaches to achieving serializable isolation. First one is actual serial execution. So the simplest way to avoid concurrency bugs is to not have concurrency at all. Process one transaction at a time on a single thread in strict sequence. For years, everyone assumed that this was obviously too slow. Then in 2000s, two things changed. One is RAM got cheap. It got cheap enough to hold entire working data sets in memory. And people realize that in memory operations are so fast, like we are talking about microseconds over here, that a single thread processing transaction sequentially could actually outperform a concurrent system that spends most of its time managing locks and resolving deadlocks. VaultDB, Redis, Datomic, they all use this approach. But there's a catch. If a transaction needs to wait for something midway through a user click, a slow external API call, or network round trip, then the thread sits idle the entire time and every other transaction is queued behind it. And for a single threaded system, that is catastrophic. So the fix for that is stored procedures. So instead of the transaction going back and forth between the application and the database, you send everything the transaction needs upfront, all the logic, all the parameters, and the database executes it in one shot, start to finish without stopping. So let's understand this with an example. Think about a hotel check-in system. The traditional approach would look something like this. The app queries the database to check if room is available. It waits for the result, then the user confirms, and then the app sends another query to update the room status. Waits again, then sends another query to record the payment. Multiple round trips, multiple waits. So if user takes 30 seconds to confirm, the thread is blocked for 30 seconds. With a stored procedure, you flip this. Before the transaction starts, the app gathers everything: room ID, customer ID, payment details. It sends all of that to the database in one call. The database runs the entire check in logic internally: check availability, update room status, record payment, all in one go, no waiting, no round trips. And all of this is done in microseconds. And then the thread is immediately free. So that's the difference. The transaction never pauses. It runs to completion in one shot. Now, the pros and cons of using stored procedures. So, the pros of using stored procedure is that the entire transaction runs without pausing, no network round trips mid transaction. And because everything runs on single thread with no concurrency, there is no lock contention at all. You can process thousands of transactions per second on a single thread. The cons is that the logic lives inside the database, which makes it harder to test, version, deploy. You are writing in database specific languages like PL, SQL, Lua, or whatever the database supports. So, not the application language that your team already knows. So that is one issue. A badly written stored procedure can crash the database thread and take everything down with it. And the whole approach only works if your active data set fits in RAM and your transactions are short and fast. So when these conditions hold, your serial execution is the best option: simple, predictable, no concurrency bugs by design. But if you have like large data sets, long transactions, high write throughput, we need a different approach. So that's where your two-phase locking comes in. Right. So serial execution only works when your entire database fits in RAM and the transactions are short. For everything else, we need concurrency, but with correctness guaranteed. That's what two-phase locking gives us. So with snapshot isolation, the rule was readers never block writers, writers never block readers. Two-phase locking is opposite. So readers block writers, writers block readers. So if two transactions touch the same row, one is writing, then other must wait. This is what makes two-phase locking serializable. Now, how does this work? So there are two types of locks in two-phase locking. One is a shared lock for reads, where multiple transactions can hold shared locks on the same row simultaneously, and that's fine. Reads don't conflicts with each other. Then the other lock is exclusive lock, that is for writes. So an exclusive lock blocks everything. No other transaction can read or write that row until the exclusive lock is released. So when you read a row, you acquire a shared lock. When you write to a row, you need to escalate to an exclusive lock. And that escalation only succeeds when every other shared lock on that row has been released, right? So if we see the example over here, row 1 has shared, transaction A has shared lock for row 1. Transaction B also acquires a shared lock for row 1. Now transaction A decides to write row 1. It requests for an upgrade to exclusive lock, but it needs to wait for transaction B's shared lock to be released. Now, transaction B also wants to write request, and it also now wants to update its lock to the exclusive lock. And now this is a deadlock scenario because A is waiting for B, B is waiting for A. So database detects it and then aborts one of them. which becomes the victim so that the other one can continue. Now, there are two phases to understand in two-phase locking. Phase one is the expanding phase where you acquire locks as you go. You don't release any of them. Phase two is shrinking phase. You release all the locks at once at the commit. And why does it have to work this way? So think about what happens if you release the lock early. Say you finish reading a row and immediately release the shared lock before your transaction commits. Another transaction could read that row, make a decision based on it, and then commit. Now, if your original transaction aborts, the second transaction can't undo what it already committed. So you have created an inconsistency. Holding all the locks until commit prevents this. Nothing built on your reads can commit until you have decided whether your transaction succeeds or fails. The performance cost for two-phase locking is real. One slow transaction holds all its locks and creates a queue of waiting transactions behind it. Deadlock detection adds overhead. Every single row access requires logbook keeping. Under heavy load, this becomes the bottleneck. And another limitation of two-phase locking is two-phase locking with row locks still doesn't prevent write skew and phantoms because those anomalies aren't about a specific row changing, they are about a condition across multiple rows. So to prevent phantoms, you need to lock what doesn't exist yet, and that's where predicate lock comes into picture. A predicate is just the condition in your where clause. So if Alice is booking room 1 between 12 and 1, the predicate is room equals 1, and the start time is greater than 12 and the end time is less than 1. A predicate locks the entire condition, which means it covers any row that would match it, including rows that doesn't exist yet. So if Bob tries to insert a booking for room 1 at 12:30, the insert matches Alice's predicate and it gets blocked and the phantom is prevented. But the problem here is every time any transaction reads or writes, the database has to check, does this operation match any predicate lock held by another transaction? And every time a new predicate lock is acquired, it checks, does this overlap with any existing locks? So with thousands of concurrent transactions, each holding their own predicate locks, you're doing thousands of condition comparison for every single operation. So that would mean O of n square complexity, and at scale, that becomes a serious performance issue. So in practice, databases uses something called as index range locks. Instead of locking the exact predicate, you lock the index entry that the predicate maps to. So in our example, instead of locking room 1 between 12 and 1, you lock the entire room 1 index entry, all bookings for room 1, regardless of the time. Now, if Bob wants to book room 1 at 3 p.m., his transaction hits that index lock and it has to wait, even though his bookings doesn't actually conflict with Alice's time slot. So Bob is unnecessarily blocked over here. But it's worth it. Why? Because checking an index log is O of 1 complexity. You just look up an index entry, no condition comparison needed. So the false positive are a trade-off that you accept for the performance gain. And in practice, these false positive rarely matter much because the transactions are short. Bob waits for a few milliseconds and then he can try again. Now, moving on to the third serializability approach, which is serializable snapshot isolation. So, two-phase locking gets us serializability, but it is pessimistic. It assumes conflict will happen and it pays the cost for it upfront. Now, what if most transactions don't actually conflict? And that's the bet serializable snapshot isolation makes. So, Serializable snapshot isolation is the newest of the three approaches. Postgres 9.1 introduced it, and the philosophy is different from two-phase locking. Two-phase locking says conflicts will happen, block early, pay upfront. Serializable snapshot isolation says conflicts are rare, run freely, detect them at the commit time. So if a conflict is found, abort the transaction and retry. So you only pay the cost when the conflict actually happens. Now, the key insight is that every write skew anomaly follows the same pattern. A transaction reads some data, forms a premise, it makes a decision on that premise, and then writes. But by the commit time, the premise is no longer true because another transaction changed the data underneath. Serializable snapshot isolation tracks these premises. So if your premise was invalidated before you committed, your transaction gets aborted and you retry. So SSI builds on top of snapshot isolation. Each transaction still reads a consistent MVCC snapshot. That part doesn't change. But SSI adds a detection layer on top. The database tracks what each transaction read. When another transaction commits a write, the database checks, did any active transactions read set include the rows I just changed? If so, flag those transactions as potentially stale. Okay, now let's understand two detection patterns through this visual over here. So transaction A, we have two transactions over here. Transaction A reads the doctor's on-call table and sees Alice and Bob both on call. At the same time, transaction B has uncommitted write, marking Alice as on off call. Transaction A reads a row, ignoring an uncommitted write from transaction B. Transaction B writes Alice on call as false. This is uncommitted. Transaction A reads Snapshot, ignores B's uncommitted write and sees that Alice is still on call. Because this is uncommitted, transaction A doesn't see this. Now, SSI tracker, the SSI notes that transaction A's read overlaps transaction B's uncommitted write, and this is a potential stale read, and it flags it. Now, transaction B commits. Transaction A's premise was that Alice is still on call. This premise is now stale, so it is going to abort that stale premise. Transaction A tries to commit, the SSI detects stale premise, and it aborts transaction A. So you can throw an error like retry again. Then the next pattern is write affects prior read. So transaction A reads all rows where on call is true. It sees Alice and Bob, right? Now, transaction B then writes to Alice's row and it tries to set Alice's record for on call as false, and then it commits. Now, the serializable snapshot isolation, it detects that transaction B's write intersects with transaction A's read set, and the conflict is recorded over here. So, transaction B commits first, and then transaction A tries to commit. So, transaction A, the SSI aborts transaction A and asks it to retry. So, the difference between the two patterns is the timing. In pattern one, the conflicting write was already in progress when the read happened, and it was just uncommitted. In pattern two, the read happened first and the conflicting write came after. So, your SSI catches both. Now, let's talk about the performance of SSI, right? At low to medium contention, SSI is significantly faster than two-phase locking. Readers never block writers, there are no deadlocks, transaction complete faster. And as contention rises, more transactions touch the same rows, the abort rate climbs. So, aborted transactions waste the work they already did. So, at high contention, two-phase locking can actually outperform SSI because the upfront blocking prevents that wasted work. Now, which approach to pick, right? So if you have high contention, then SSI abort rate is high, work is wasted. So two-phase locking is preferable. Medium contention, SSI abort rate rising. So like advantage of SSI is shrinking and advantage of two-phase locking is going up. And if there is low contention, then you should go ahead with SSI. Now, if you have read heavy low contention, then go with SSI. If you have write heavy high contention, two-phase locking might be a better option. And serial execution would be a better option for in-memory workloads with short transactions where you can afford to partition your data. And this brings us to the end of chapter 7. Transactions are an abstractions. They hide a lot of complexity, but these these abstractions can be leaky, and that leak shows up at the wrong moments. The database doesn't tell you when you have picked the wrong isolation levels, and it doesn't warn you when you have hit a right skew scenario or you have missed some of the edge cases. So your data just quietly ends up wrong. So, what this chapter gives you is the vocabulary to think clearly. We have covered the failure modes a transaction protects you from, the asset guarantees, what each one actually means, the anomalies of different isolation levels, and we have talked about different approaches to achieving serializability with different trade-offs. The practical takeaway is most applications run on read committed and snapshot isolation by default. That means write, skew, and phantoms are possible. If your application has invariants that span across multiple rows, for example, like you have scenarios like we talked about room booking scenarios, on-call schedules, inventory counts. You might need serializable isolation, or you would need to explicitly use select for update to log those rows you're checking. So that's it. Next is chapter 8, where we talk about distributed transactions. So hope to see you there.